Okay, welcome everyone. Tonight's presentation is on the black hole closest to Earth. This is kind of a follow-up to a presentation 2 weeks ago about black holes, in my opinion, just being kind of a flavor of quark stars. But this actually is something that came up this week, and it was so confusing to the media that they couldn't get straight. So which black hole is closest to the Earth? The one that we found 2 years ago that's closer, or the one we found this week that was announced this week that was actually discovered late last year that's a little farther away? And so to clarify it, I had to do some research and go, oh, I get it. And even some of the people that are on the internet that do presentations didn't get it right. So black holes. If a star is sufficiently massive towards the end of its life, when it runs out of fuel and can fuse nothing other than iron, it will collapse. And if it's big enough and massive enough, it will collapse into a black hole, a singularity, where math goes to infinity. That's the disagreement I had last presentation. Was mathematicians are aware of infinity, understand it, but don't really like it because it usually means you haven't quite figured something out yet.
Division by zero.
Yeah. So in galaxies, there are different sized black holes. There are the black holes at the center of galaxies, the supermassive black holes. And then there are smaller, but still large enough stars that form black holes, and they form smaller black holes. These are black holes that wind up being smaller than the diameter of our sun, but having roughly the same gravity as our sun, and they refer to them as stellar mass black holes. According to current theories, a galaxy the size of the Milky Way that has roughly 100 billion stars. Now, we know that it's currently more like 120 billion, so the numbers go up as we can observe better, but there should be 10 million plus stellar black holes in our Milky Way. Now that's the prediction from the calculations based upon observations, and we have yet to find anywhere near close to 1 million black holes, stellar mass ones, in our Milky Way galaxy. So one of the questions in astrophysics is, where are all the other stellar mass black holes? They don't have an answer for that at the moment, but they're thinking real hard on it. So if you have a black hole and it's not feeding, in other words, it was all by its lonesome and went boop and became a black hole of the stellar mass variety, there's nothing left to feed on because it consumed all that when it became a black hole. And because it's not feeding, it's called dormant. And dormant just means it's not spewing out electromagnetic radiation. There's no EM emissions from it. There's no radio, infrared light, ultraviolet, X-ray, or gamma. And since that's the only way we can observe things, we can't observe these. They're literally a black spot in the sky. And if they're that small and that far away from us, we're not going to see them easily. They would have to go in front of something else that's bright, and then we would see the black spot. Or something would have to stray too close, and they would start feeding, and then we could see the accretion disk around it, where that gas and plasma and dust and everything got heated up and started glowing in infrared, and oh, look, there's a black hole. But a black hole, even a stellar mass one, is a huge gravitational source. So if something gets nearby it, even if the black hole is dormant and not feeding, it will orbit the black hole. So we can see something orbiting something we can't see. And so we think of that as, that must be a stellar mass black hole. So recent, as in like late last year, there was a discovery, and confirmed by a second observation, but not an observation from others, just a second observation from the same site, that there is a stellar mass black hole about 1,560 light years. For those people that measure things in miles, that's 9.36 quintillion miles. So you can think of billion, trillion, quadrillion, quintillion. So it's nowhere near us from a hazard of black hole being near us perspective. It's just out there, and we've concluded that it is there. It is in the constellation Ophiuchus. It was confirmed by the Gaia Observatory, not the black hole, but the star closest to it that's orbiting it was confirmed by Gaia. And they just said, well, the spot that we can't see, that's where the black hole is. So Gaia proclaimed it to be Gaia Black Hole 1 or Gaia BH1. Gaia never saw the black hole. It saw the star that's orbiting it, and it assisted in the orbital calculations, but it never saw the black hole. We've never seen this black hole. So the picture you see there is an artist's rendering, and the distance from that Earth-like or sun-like star to the black hole is imaginary. The black hole would be far smaller, and the distance in order to avoid feeding by the black hole would have to be much farther away. But the star is in Ophiuchus, and it's in the Hipparcos catalog as 85537, and that star is actually visible naked eye. It's 5.4 magnitude, so it's right at the fringe of people with good eyesight. The black hole was identified in a monthly notice of the Royal Astronomical Society. So that is the publication that announced the theoretical statement that this is a black hole. Based upon the orbit of this sun-like star that is orbiting the black hole that they can't see, the postulation is that it is a stellar mass black hole. The size of the black hole, based upon the orbital characteristics, is about 28 kilometers or 17 miles in radius, and that's based upon the Schwarzschild radius of it. The actual observation of the orbiting was done by the Gemini North Telescope in Hawaii. That's an infrared telescope operated by the U.S. National Science Foundation's NOIR lab. So that's National Science Foundation, National Observatory for Infrared. To date, as in right now, this is being publicized as the closest black hole to Earth, 1,560 light years away, not nearby. We don't have to worry about it affecting us anytime soon, but we can study it. We can learn more about black holes by, hey, it's close enough. So is there an even closer black hole? And I looked at the news media reports of this, and I thought, oh, it's back to FUD. Be afraid, be very afraid. A black hole is going to come and swallow us up. Okay, so in 2020, they hypothesized using these same orbital calculation concepts that there was a stellar mass black hole orbiting nearest to HR 6819. And it's actually a triple star system, two regular stars of roughly sun size, and a black hole that's a stellar mass black hole. Now, the two stars are magnitude 536. They're in the southern constellation of Telescopium. So they'd be easy to split with even an amateur telescope and do orbital calculations. And it turns out, if there was a black hole there, it would be about 560 light years closer than Gaia BH1. How did they find it? Well, they were actually looking for black holes in X-ray binaries. And since these other two stars were spewing X-rays, they thought, must be a black hole nearby because they're spewing X-rays. Well, they didn't find any X-ray binaries in this particular star system, but they did find that one of the two stars appeared to be orbiting a third unseen object. So they announced, we found the closest black hole to Earth. That was in 2020. In 2022, after further observation, they discovered that now, not even 3 stars, it was just 2 stars. And one of the stars was so very much lighter that its orbit was being jerked around by the other star that was elliptical. It's a 2-body system algorithm, and one of the bodies is circular and the other body is elliptical, and it makes it look like the orbit's being dragged. But just as an elliptical orbit around something like the sun, some places in the orbit it moves faster, and other places it moves slower. And they thought that was an indication that there was a black hole there, but no. Thus, I put it in the category of supposedly closer, but no cigar. You might find early internet articles talking about HR 6819 being a black hole, but the internet never forgets. And even astrophysicists like Dr. Becky proclaimed this to be the closest black hole to Earth. And later on, turned out it wasn't, but she hasn't gone back and retracted the video or updated it to correct it. So this week, having the announcement of Gaia BH1, put a pushpin in that, and we'll see how long that stands up to further scrutiny. It'd be nice to know it's a black hole that we can use for target purposes, but so far it's just postulated based upon observations of being a stellar mass black hole at 1,560 light years. So I've got a couple of postulations in here. Postulation 1 is black holes, when they're not feeding, not known to emit electromagnetic radiation, no radio, infrared light, UV, X-ray, or gamma. They're still dealing with energy production as their quarks change, as they go from a neutron star to a quark star to a black hole. And my postulation is their means of exchanging energy, of having an energy messenger in the absence of electrons is, well, they can't generate photons, so how about gravity waves? Because gravity waves are a form of energy, but they're generating gravity waves that are low amplitude, not high power, and they're very high frequency, so they're quick to oscillate. The current gravity wave detectors that we have, LIGO and Virgo. LIGO is actually 2 detectors, one in Louisiana near Livingston, and the other one in the state of Washington in the US near Hanford. And they're these giant, 4-mile long L-shaped things, and they run a split laser beam down them to mirrors, and the distance between the front and back is to within the width of a proton, identical. And when gravity waves come through the Earth, they stretch one direction or the other. The fabric of space-time actually becomes elastic and stretches out and then collapses back. So we can see this ripple in either of the 2 L beams because the distance changes, and because we're running an interferometer, when the 2 waves are precisely the same, the detector sees nothing. They cancel each other out. But when one is a little longer than the other one, or a little shorter than the other one, then the detector sees a difference, and the light detector detects something. So, interferometry. But if you increase the signal sample rate, in other words, the number of samples per second, from millions of samples per second to nearly billions of samples per second, as the Nyquist theorem says, you can see a higher frequency because you can detect all the peaks and valleys as opposed to skipping them because you're not sampling fast enough. And the second thing is you can use newer technology amplifiers to boost the signal even higher. You can go from having vacuum tube amplifiers to having digital amplifiers and signal noise elimination. And now you can see lower amplitude, higher frequency gravity waves. And they're talking about the 2 different observatories of LIGO going from seeing one gravity wave every 2 years to seeing multiple, don't know how many multiple, but multiple gravity waves per year. I think when they get the gravity wave detection to the point where they can see high frequency, low amplitude, they're going to find that all those neutron stars and all those quark stars and all those black holes are producing a gravity wave background hum. Just like the cosmic microwave background, they're going to see a gravity wave hum in high frequency, low amplitude gravity waves. So that's my postulation. We'll find out. LIGO, both observatories are going to be updated and operational with their more sensitive mechanisms in 2024, so next year. So we got to wait a while. The second postulation I have is black holes don't emit electromagnetic radiation because they've run out of the mechanisms to produce them. Everything, as the saying goes, everything went to hell. Well, in a neutron star to a quark star to a black hole, everything went to quarks. And when everything goes to quarks, you've got no protons, you've got no electrons. You had neutrons until the neutrons got so compressed they split up into a quark soup. And then you had different kinds of quarks. And then as you had more strange quarks than other kinds of quarks, even the quarks were letting you down as to, now how are you going to send out waves of energy? Well, we'll send out photons. Where are you going to get the photons from? You have no electrons. Well, my postulation is the reason why black holes are dark is not because gravity holds in the photons. It's because it can't generate photons. That's like saying, I'd really like to have ice in my drink, but I have no ability to create ice. Therefore, all my drinks are warm. Well, what if you had a refrigerator? Well, I could put it in the refrigerator and get it cooler and then take it out of the refrigerator and I would be drinking cool liquid. Well, how about a pulsar? A pulsar is a rotating beam generating mechanism. So if I could find a pulsar that was spinning at the right rate, at the right angle, such that its beam swept past a stellar mass black hole, all of a sudden, without feeding mass, without feeding on protons, neutrons, and electrons, the black hole would suddenly have the stuff. It had photons to generate photons. So maybe if you have a subatomic particle beam from a pulsar sweep by a black hole, the black hole might go burp and spit out a change in gravity waves. So maybe the low amplitude, high frequency gravity waves would suddenly become higher amplitude, lower frequency gravity waves until the beam swept by and all of the energy was converted into more quarks, and then it would go back to not emitting again. So that's postulation number 2, is that I think if we can find our beam energy source as a pulsar, and we can find a pulsar that sweeps past a non-feeding black hole, and we get LIGO enhanced to be able to catch these more elusive gravity waves, we might find that, producing gravity waves, and when you feed it energy in the form of photons, it will change the kind of gravity waves it produces. And in fact, if you give it enough of a pulsar burst, it might actually produce gamma or X-ray radiation because it has just enough energy. So that's the postulation. Now, if you have a black hole that provides energy, if you have a pulsar that provides energy to a black hole and it emits a burst of gravity waves, that could affect, within range, neutron stars. And remember what they're saying about gamma ray bursts being, well, that may be stellar quakes on neutron stars. And if you've got a gravity wave rippling through a neutron star, that may be just enough to cause, fraction of a millimeter quakes on a neutron star which would cause it to produce a gamma ray burst, which might also explain why gamma ray bursts are elusive and not predictable. So something to think about. And a postulation from our 2 weeks ago presentation, are black holes merely quark stars? The degeneration of regular matter of dwarf stars into neutron stars, into quark stars, into strange quark stars, and I postulated the next degenerate level is top quarks. Well, I did find out that Fermi Labs actually generated singular top quarks and watched them dissolve. Well, if you generate enough top quarks, maybe they don't dissolve. But that's something to think about. So let's say we have a black hole. It's not feeding, so it has no way to let the energy out as top quarks come into being. So it lets it out as gravity waves. If that is actually a mechanism, then you wouldn't need Hawking radiation, because the black hole will dissolve slowly over time, but much quicker with gravity waves than with Hawking radiation. And if you can have gravity waves as the energy outlet for stellar mass black holes might degenerate and dissolve all on their own. And if that's the case, that might explain the absence of why are we missing millions of stellar mass black holes? Because they're not there anymore. But what it might explain is rogue stars. We're finding more rogue stars than we thought were possible. A rogue star was believed to be, you've got two stars orbiting one another, and one just has a little more centripetal oomph and slings the other star out of its solar system, and therefore you find a star moving transverse across the sky at high speed. Well, if you have two stars and one of them becomes a black hole, and over billions of years that black hole gets small enough that it no longer has the mass to hold its pair star, and it slings that pair star, that would explain why you have lots of rogue stars, because they were once part of a binary. And one of the stars in the binary became a black hole, dissolved into a quark star, and then lost just enough gravity through gravity wave emissions that it slung it free. So that might explain why you have so many rogue stars and so few stellar mass black holes. But there's two postulations about angles. One is when a dormant star is producing gravity wave emissions, do they come out in kind of a beam pattern of gravity waves like a pulsar, or do they come out spherical, like as if you were ringing a bell? Well, I think they come out spherical because nothing's holding them back from not being spherical. And when a dormant black hole gets an influx of photons, what happens? Well, the frequency is dictated by the top quark degeneration. So I think it's more the energy level, the amplitude that changes and not the wavelength. And in conclusion, not everything that exists is directly detectable by our one and only capture of electromagnetic emissions. We're not going to see it in radio, infrared light, I should say UV, not UR, ultraviolet, X-ray, or gamma. Some objects are not visible in the spectrum, so we have to look at them through other means, like we watch the orbit of something and then presume the thing we can't see must be a black hole. But there should be roughly 10 million or so stellar mass black holes, plus the supermassive black hole at the center of the galaxy, and we're not finding them all. So I'm waiting for the LIGO upgrades to be able to see low amplitude, high frequency gravity waves. And once we have that ability, maybe if there's a pulsar sweeping by one of these stellar mass black holes, it changes its gravity wave emission. And the internet never forgets. So whether I'm wrong now or I'm right later, the internet will probably have a record of it, much like that video of Dr. Becky saying, "We found the closest black hole to Earth." and now we know not.
Very nice.
And so I provided some links to all the topics that I spoke of. I'll leave that up there for a moment that people might want to capture it once we're in post-processing. And now, any comments or questions? The one thing I will say is, hey, there were no formulas. And aside from one very large light year measurement, there was no math. So it was all just observational evidence and postulations. So we shall see how well that spaghetti sticks on the historical wall. Next week, I'll try and find something that is a little less esoteric and doesn't include any postulations. I'll try. But I won't know until I get there. And we're just now at 11 o'clock. Boy, that was a fast presentation. Only had 13 slides.
So are these people like Dr. Becky saying this is the closest black hole, or it's the closest known black hole?
No. In 2020, there were actually, like I said, Royal Astronomical Society actually posted in their bulletins, it has been confirmed that this is a black hole. Not this one, the previous one from 2 years ago. And it took 2 years for other observations to come out to say, I don't think so. You guys got it wrong. So this is a new publication for BH1, and it's from the National Science Foundation, because that's your tax dollars that were running the observatory in Hawaii from the National Observatory for Infrared Astronomy. So they're all about promoting their own capability, but there hasn't been a lot of other observatories that have corroborated this yet. So it could be the one in 2020 was closer than this one is, but turns out not really a black hole. This one that we currently think is a black hole, and we've got government pronouncements of it being a black hole, we might find out 2 years from now, nah, not really. So I hear what you're saying. I understand what you're saying. I know this is the only evidence, the only observations you've got right now, but I'm willing to say the verdict is still out. But the funny one was the article, somebody published this week an article, and they got the two observation announcements wrong. They pulled the one from 2 years ago and did an announcement this week, but it was really the one they announced this week that they wanted to do the article on, but they didn't. They did the one from 2 years ago that turned out to not be a black hole. So the general media sometimes picks the wrong thread. And because you see things like, well, a publicly noteworthy astrophysicist said it was the closest black hole to Earth. Well, she hasn't come back later after it was proven that not really, and corrected her video. Because I watched the video from front to back. No. So sometimes in the absence of higher quality observations or more observations, science can make claims that are later proven not accurate. And that's expected. That's how science works.
Yeah.
And I'm more than willing to say, yep, this week, I hear what you're saying. That's a stellar mass black hole. Good to hear it. Now let's go find a pulsar that can beam it. Sweep the beam past it and see what happens. And let's get LIGO upgraded so we can detect those gravity waves. I'm all for all that stuff. So, yeah. Science marches on, as the saying goes. Okay. Anything else before I stop recording?
Nope.
Okay, let me stop sharing. And stop recording.